welcome back to the Algebraic Geometry Seminar. Today we are finishing up normality and factoriality, aka Vakil 5.4. So what we did not cover at the end of the last lecture were some of the examples and exercises on the last 2 pages of chapter 5.4. So that is what we're going to focus on for now. If we get to quasi-coherent sheaves, that's awesome. If we don't, whatever. Okay, so recall that the scheme X is normal if and only if its stalks are normal. And that this means functionally that OXP is an integral domain which is integrally closed. Okay. And so, trying to make sure that there's not something else going on here. And this is equivalent to no zero divisors plus zeros in the fraction field of stock. Lie in the stock. Lie in the localization. And zeros of monic polynomials. Monic irreducible polynomials. Zeros. Okay, I will also recall that factoriality implies normality. So if we can show that the stalks are unique factorization domains, then we get normality. Factoriality is okay. So with these results on the board, we want to show that the following schemes are normal. So n is a square-free integer congruent to 3 mod 4. What does square-free mean? Can you Google that for me real quick?
Yeah.
Square-free integer.
square free integer is a whole number not divisible by any perfect square other than 1.
Wow. Okay.
So I guess like 6 is a square free integer.
And there does not exist x and c x squared divided n it's a normal scheme. Okay. So let's work this out for a specific example. You said 6 is a square free integer?
Yeah.
Okay, it's not congruent to 3 mod 4.
7's a square free integer.
7's a square free integer. Okay, cool. So let's consider, and if you can just look on the recording in a second and just tell me where the drop-off point is. Can I write here?
Yeah.
Here? Okay, got it.
Actually, yeah, you can. Sorry.
I'm just going to say that that's the line.
Yeah, that's just easy.
Yeah. Okay, so we're going to say x squared minus 7, because 7 mod 4 is 3, and it's prime. Okay, is normal. I'm just going to call this scheme x. And note that little x and big X are two very different things.
Why don't we just change the name of the scheme?
Because I can do a curvy X.
Oh, okay.
That seems like a kind of bad answer, but okay. So first, let's consider what we're saying here. So spec z over x really should look like x minus an integer, right?
What's that?
Spec z over x should look like x minus an integer.
Should be.
Because those are the prime ideals.
Yeah.
Certainly x squared minus 7 is a prime ideal.
Yeah.
Of course, this converts to roots which are not in spec z. Hold on, I'm just gonna. Let me look for something here. Spec z. I'm gonna grab my laptop so I can like Google things and check math stack exchange.
Okay.
And also keep track of time.
Yeah.
So you get everything.
That's a good idea.
Okay. Spec z over x. And then we want to determine what goes weird with x squared minus 7. Yes. So so spec z breaks down into height 1, height 2, and height 0 ideals. Height 0 being the generic point, height 1 being irreducible elements in z over x, or equivalently prime numbers which are irreducible in q over x by Gauss's lemma. And then height 2, which are maximal ideals. which I'm a little confused by. Oh, that's why that doesn't make sense. It has like -3 upvotes on math stack exchange. Oh, there's a picture of this by Mumford. Never mind, unsecure page. All right. Whoever was trying to fish mathematicians on Math Stack Exchange did it successfully. They got me. Okay, so generally, spec C is the tensor product of Z with Z over X. And so this ends up giving us the generic point, and then points which are irreducible over FP. And so we end up getting copies of finite fields. And then we end up at the very end with just irreducible polymers. And this is dimension 0, that's dimension 2, this is dimension 1. It's worth noting the construction of these finite fields comes from ZP mod fx, which is GFP to the degree of f, right? So this is our general construction from field theory.
Yeah.
And this makes sense. Like
Yeah.
this does tie together some things.
Right.
But then modding out by x squared minus 7. When we're saying that x squared minus 7 is congruent to 3 mod 4, I'm almost wondering if it's saying that this would be the finite field to, no, it would be the finite field that doesn't make sense, it's mod 4. Because it's, hold on, mod 4. Okay, we can compute this on a level of Galois group. And just regular ZP automorphisms. So we have x is the square root of 7, so so we end up getting an extension of degree 2. This is a simple extension. So
wait, how do we get the degree 2?
This is like from Galois theory. It's a degree 2 root.
Oh, okay.
Yeah. Like if we're thinking of this as a k-vector space,
Yeah.
right? We have a basis 1, and then we have a basis square root of 7, and then square root of 7 squared.
Oh, okay, yeah. Sorry, I'm a little rusty from that.
No, you're good. That was like a year ago. And then to compute the automorphism group, we want to permute all of z, and we want to fix z, and we want to permute the square root of 7. And I think that ends up being a trivial extension, or a trivial Galois group. I know I'm doing something weird here.
Yeah.
This feels a lot more vulnerable standing in front of the board than just being on the iPad.
Right. I have a professor who does his iPad notes projected to the big screen for $250.
That's
I really enjoy that.
Huh. So then maybe this is just an irreducible polynomial here, and then it becomes interesting in just characteristic P. So really what we're saying is that, thinking in terms of spec, we're saying that in a ring spec, A plus 7 is the map into from A spec C for X to the scheme. Okay, so we're sending prime ideals of this form to something reduced x squared mod 7. So what can we not zero out in terms of x squared mod 7? We're trying to show that the stalks, so localizations by prime ideals, are an integral domain which is integrally closed. So what we want to do is we want to take an arbitrary prime ideal localized by that prime ideal. We want to show that it's an integral domain which is integrally closed. I'm going to erase this top part.
Okay. I have it all down.
So then the stalk at P is the set of Q in our scheme such that is not contained. pretty sure here. Let me grab. Yeah. These are all the things that don't vanish. Yes. Okay. And then we want to show that this is an integral domain in X. So we want to say something about the fact that Q is really A over B, where B, maybe it's not B corresponds to A over B, where B is non-zero on P. Well, P in X has to have that B is not 0 or the ideal x squared minus 7. Right? Or rather, it does not correspond to it. I keep writing the equal sign. Hopefully it's clear for the camera. It should not be an equal sign. It should be does not correspond. And really what this is that B is not the square root of 7. Okay. And then we want to show that does not exist in H in OXP with QH is either 0 or something over square root of 7. Okay. Does this seem consistent with your notes so far?
Yeah.
Is my definition for OXP correct?
I believe so.
Okay.
That's in a different notebook. This is kind of a newer one because I ran out of space to go.
Okay.
Sorry.
Have you marked up your rising C copy at all?
Not yet.
Okay.
That is on the list of things to do, but there are a few more pressing things. Yeah. But I could find it. I mean, there's an appendix here.
Yeah, that's just my only concern is that I'm using the wrong definition here. And this is something I should know. I'm just really tired.
Here we go. OXP is page 46.
Oh.
on
The appendix
sheets.
exists.
Yeah, that's what they did. OXP.
It's a collection
It's the
of.
stalk of OX writ at P.
Yep.
It doesn't give us the OX is a sheaf of rings.
I wonder if this has definitions in the back.
No, I doubt it.
No, it doesn't.
So, ring of regular functions localized at P. Dude, this should not be throwing me for such a loop right now.
I know.
To the viewer, please have a smidgen of grace here.
Yeah.
Retired undergraduates. And I'm moving this week.
Oh, where are you moving to?
New place.
Nice.
Okay. Implicitly, this makes sense. I think that this is correct.
Yeah.
Because the whole idea is that we need our denominator to not zero out on P.
Mm-hmm.
So we need it to be Q and X corresponding to a rational function which does not divide by 0, and so B is non-zero on P. And so it's the set of things corresponding to prime ideals which are not containing the vanishing.
Yeah.
So I think that this is correct.
Yeah,
I'm really trying to not screw this up.
Right.
So we want H, so this is to clarify, this makes it integral domain, and then we want to show that it's integrally closed, which is that zeros of monic polynomials in the function field of local ring.
He says that our argument may also show the result when 3 is replaced by 2.
When 3 is replaced by 2. Oh, that's for the same reason that 6 works. Yeah.
Okay.
I don't know the reason, but I
Yeah.
know that it's going to relate back to the fact that 6 would have worked.
Okay.
1 plus the square root of 2, or 1 plus the square root of n over 2 is integrally closed. Right. The other thing we want to show is that the zeros of monic irreducible polynomials in the function field lie in the local ring. That part's actually easy. That part's actually really easy.
Yeah.
I think part 1 is also pretty easy. I'm just kind of moving slow today.
Yeah.
I spent a lot of time writing my honors thesis. But we want to show that, so zeros of monic polynomials that are irreducible in the function field are the things corresponding to vanishings of the numerators.
Yeah.
And that is, in fact, just all of spec C x squared, or x squared minus 7.
Yeah.
And so we want to show that the zeros of that lie in spec Z over x. That is marginally more difficult. Hold on. So it's not saying that they need to lie in spec C over x. It's saying that they need to lie in spec C over x mod x squared minus 7. So we're interested in any vanishing in the numerator that lies within local ring. Yeah, is the second one not just like I don't even know how to formulate it because it's so there. It's saying that A, which is something corresponding to the vanishing of Q, needs to vanish on Q.
Could you say that again?
Sorry,
So-
my mom was texting me. so-
No worries. So Q is a prime ideal
Yeah.
that doesn't vanish on P.
Okay.
Then the function field of things that don't vanish on P
Yeah.
are rational functions corresponding to things that vanish on Q.
Okay. I don't know how we can get an integral domain out of that, but.
No, this isn't for integral domain, this is for
Oh.
integral closure,
Oh, okay.
which is saying that Q vanishes on Q, or things of the form A over B are functions which vanish on Q as long as P is not contained in Q. And that's the definition of the thing. But I'm trying to make sure that we're using the x squared minus 7 bit, right?
Yeah.
Like what fails if we have a non-square free integer that is 3 mod 4, right? So we could consider like n is 4, x squared minus 4 gives us the square root of 2, right? That is still technically irreducible over
Yeah.
spec-z over x, except it is not reduced. Is no non-zero nilpotence? Yeah, because then it's not reduced.
Okay.
I don't know if that even matters. Just check, is it still recording?
Yes, it is.
Okay.
I'm trying to think about like other square free 3 mod 4s.
Well, for 4, we get something interesting, because we can get 2. Oh my god, it's not the square root of 2.
What?
X squared minus 4 does not factor with the square root of 2.
Oh yeah.
Okay.
X squared minus 4 is 2.
Yeah, it's 2. It's plus or minus 2. And so with plus or minus 2, then we are excluding x minus, then this is not a PID.
Mm-hmm.
Or not PID. Not a principal ideal.
Yeah.
And so it's, I think it's just not a scheme. Right? Because we need this to be irreducible.
Yeah,
Isn't that the case?
I think so.
Let me look at our construction of a general scheme.
$121 also works.
11 squared?
Yeah, because that's not made up of
11 mod of 4
is
3. 11 is prime, so it's square free.
But does 121 count as like, oh, it itself is not square free because it is a square?
No, but
Or
oh yeah. 121 wouldn't work because that's not square free.
Right.
But 11 would work.
11 would work.
Is 11 3?
No. 11's prime.
No, but mod 4. 11
Yeah, it
is
is.
3. So 11 works.
Yeah.
121 doesn't.
Right. Oh, so square free, really, what square free is saying is these are all 3 mod 4s that are irreducible.
Yeah. Yeah, but where does the 3 mod 4 come in? Is that a condition for primality? Like any 3 mod 4 square free integer is prime? hold on, let me
As I'm
Google
going through it, I'm figuring that out.
that seems like that's the trend here.
Because it goes 3, 7, 11.
Square free.
No, 15 isn't prime. 15 is square free, not prime.
But it factors directly into primes with no repeated factorizations.
Okay, yeah.
Our square free integers, which are 3 mod 4 special.
15, 23. Nope, 27. Oh no, 27 is not square free. My
Yeah.
bad. 27 is a cube.
Yes, because
31.
they can't be expressed as the sum of two squares. Okay. Yeah, so the whole point is that you don't end up getting repeated roots.
Oh, okay.
And so the trick is that this is a reduced scheme.
Yeah.
And it's an integral scheme.
Okay.
And reduced plus integral no. Oh, that's painful. Integral schemes are irreducible and reduced. This is just one way to get an integral scheme.
Yeah. But
So-
if we say it's an integral scheme, doesn't that help us prove?
Well, so it does take the integral domain piece out of the way for us. The thing I'm trying to wrap my head around and make sure that I'm not doing it wrong is why, in terms of showing that zeros of monic polynomials in the function field lie in the local ring,
Yeah.
that seems like a total no-brainer.
Yeah.
What am I missing?
I have no clue.
Okay. I'm just trying to generate counterexamples here of
Are
like.
are you sure it's like with the monic irreducible?
Yeah. That's what it says in the book. That's the definition of integral closed.
Yeah.
Right?
Yeah, but are you sure you're looking at it in that context?
Yeah.
Okay.
Yeah. A is an integral closure if
Yeah.
if the roots of monic polynomials lie in.
Yeah.
Right? Because it's okay. Hold on. This is good. So A is F over X.
What is that?
F in A, the polynomial.
No, A is integral
Oh,
closed.
yeah. If that's all. It's all roots in A. So we're putting a polynomial and it's not just the polynomial ring, I think. Hold on. I'm glad you called me on that. The zeros are in the function field. That was a terrible. Okay. So we want to put a monic irreducible polynomial in the polynomial ring over the local ring. The local ring looks like prime ideals. Polynomial ring of the local ring is just z, because those are the functions. Right?
Could you repeat that?
the polynomial ring associated to the local ring,
Yeah.
as like if this is A, hold on,
Yeah.
let me annotate this with color. Then the local ring of, the ring of functions would be Z, because those are the functions on spec,
Yeah.
right? So then we want to pick integers, which are, now here's where I'm getting confused, and where I think that the definition is that we're using is not correct. So let me go ahead and Google this. Let's see. Oh,
What?
we were doing this way harder than it needed to be.
Lovely. Probably because we could have just chose 3.
No, it's actually the factoriality implies normality.
Oh. Yeah.
So okay, the way we're supposed to do this is we're supposed to show that this is a unique factorization domain, which means that we can put anything in it and we should be able to get a unique factorization by units. And then the unit in this case is going to be or would they be primes or units in this case? Is it different for spec? So Gauss's lemma says that if we have a unique factorization domain that's just a regular ring, then that ring is a polynomial ring, is a unique factorization domain. Z of x is U of D. It's preserved under quotient. Yeah, this is Z joins square root of 7. The quadratic integer line for Q joins square root of 7. Finite 2 to 1 cover. Okay, gets way harder to do it.
Oh boy.
The way we were trying to do it. Yeah, we were on the right track.
Okay.
So, okay, let me write out where this was going, and then let me maybe, so, oh, this is spec. Z mod square root of 7. Okay, and then here's where it gets weird.
Yeah.
So this has a natural inclusion, and that is what it is, right? Hold on. I'm sorry.
Good.
Yeah, spec that. Yes. Yes. Okay. So we have a natural inclusion to spec Z that is just taken by only looking at the units of Z. Right, keeping in mind that this is prime ideals of A plus square root of 7b A b Z. Well, prime ideals of this are going to look irrational. Things come in pairs, so we have Galois correspondences, and so oh, so this actually is conjugation, right? So because you have identity and then you have plus or minus roots for monic irreducibles.
Yeah.
Like if you had, like, okay, Galois theory theorems here. So if we have if f is irreducible over Z, then it's irreducible over Q. Then we have that if if F is monic has AI and Q, then F irreducible if and only if BI are irrational. And so this means that they come in pairs, called conjugate pairs. We talked about this earlier, the example going like so. Hey Jack, fair warning, we're recording a thing.
No worries.
No worries at all. I just want to give you the heads up.
Perfect, thank you.
So we have our Galois correspondence here going on to pairs of roots, and so then we end up getting that monic irreducible polynomials must either be linear or quadratic. Quadratic ones factor in pairs of square root of 7, and so the Galois group is either the identity or the conjugation.
Yeah.
Then, where we get from this back to the idea of inclusion, is that prime ideals of, this is semi-different, but it does show up in a second. So prime ideals of this look like either prime ideals on A, or ideals which correspond to roots of square, like x squared minus square root of 7, which are power products of this.
Okay.
So then the injection to spec Z comes from this first component, which is the identity part of the Galois group. And then our conjugate pairs get left alone, where this comes down to unique factorization domain. If we start by trying to show that it's an integral domain, we are given that that this Galois group corresponds to Q over square root of 7.
Oh, okay.
That's the important thing that lets us use the Galois theory, because I just realized that it needs to be a field. Right, but
Yeah.
irreducible over Z means irreducible over Q.
Yeah.
And then what we want to do is we want to look at a bunch of things mod P, and we say that if a polynomial zeroes out like and is a vanishing in spec C as a point on a function mod P,
Yeah.
which is a stalk, then that zeroing out should be either unique or a correspondence of plus or minus a root.
Okay.
So if we can get it down to plus or minus a root, then that works. I don't want to write all of that out.
Yeah.
So I think that talking the tough way through kind of works.
Yeah.
But in terms of showing that it's a UFD, I think I have an equivalent definition that's going to be nicer to us in either the past lecture every irreducible element is prime, every height 1 prime ideal is principal. Okay, that's the one that we want to use.
Okay.
Every height 1 prime ideal is principal. So that shows what we want. Is it cool if I erase all of this? All right. Is it clear on the camera? Like, is it focused?
Hang on, let me see. Yeah, it's all good.
Okay. Go ahead and erase this thing.
Just a heads up with time, it's 35.
Okay. Yeah, so we'll just do this one exercise today.
Should we leave time though?
Okay. So, want to show X, no,
OXP.
OXP is UFE, i.e. every prime ideal of Kroll dimension 1 is principal. Okay.
Wait, what's H plus 1?
No, height, sorry. Okay, keep in mind, we said way earlier that OXP looks like the generic point, that's dimension 0, and then finite fields, or rather P and a function mod P, that is dimension 2, and then dimension 1 is just irreducible polynomials over Z. So prime ideals height 1 is the set f of x, where f is irreducible over z of x mod. Okay, so then we said that this is just z over square root of 7. And then I'm going to pull a result from field theory out, and I'm going to say theorem simple extensions of integral domains? No. Oh, I know what it is. So Gauss's lemma bridge is us here.
Yep.
Irreducible over C means irreducible over Q. Irreducible over Q means that prime ideals over Q, simple extensions of fields are good. And since nothing that we did involved explicitly 7, but rather the condition congruent to 3 mod 4, square free, this does work, although it is not written very nicely.
Perfect.
And that took a difficult amount of time.
Yeah.
That was a difficult problem.
Yeah.
A lot of fun though.
Yeah.
All right, I think that's good for the lecture today.
Alright.
Since we got to run a miv.
Great.
Thank you for watching. We will be back
Thursday.
Thursday.